Welcome, everybody. I hope you can all hear me. Still trying to figure out all of this Zoom stuff. And I have to say, it's very strange just writing to a blank screen. So I have my GSIs on the phone on the side. So if one of the GSIs can text and make sure that you let me know if there's any problems, that would be great. I'm going to try something to start. And I find I understand that you may not want to put video on, but this idea of just talking to a blank screen is very odd to me. So, what I'd like to ask you to do just to start is to put your video on. I'm going to put the gallery view on so that we can all see each other. So, I'm going to stop my share. And then in the upper right, if you put gallery view on, you'll see everybody. And let's just start by creating a little bit of community. I'll go back to sharing my screen. And if you're more comfortable, you could turn off your video. But I am loving this. I'm loving seeing all of you. And I'm going to try something else. I am going to temporarily unmute everybody. And on the count of three, I want everybody to say good morning. Let's see if that works. 1, 2, 3.
Good morning.
Morning.
Oh, felt wonderful. Thank you. This is a very strange thing to be doing, but it's the new norm. So we're going to try a few different things today. We're going to try to use poll everywhere to try to get a little bit interaction. We're going to see how that works. I'm going to try a few different ways of doing that, and we'll see what happens. We'll see what happens. So let me go back to sharing my screen. See if I can flip back and forth. Now, okay. So today's lecture is about passive cooling. So what I'm going to encourage you to do when I'm not doing a poll is to, let's see, can you guys, I'm having trouble with my second screen. Sarah, if you can unmute yourself so you can hear, do you guys see the presenter view or do you actually see?
We also see your notes.
Yeah, let me see something. I'm having trouble with my second screen. Let me just reconnect that. And let me try that again. Sorry, I tested this over and over again this morning. And then that looks better. Is that better?
Yeah.
Okay, thank you. So passive cooling, we've heard about passive solar heating, where the sun is the natural heat source. So passive cooling, what does that mean? That's where we have natural heat sinks. That's where the heat is going to go. So we're going to talk in a moment about what those different natural sinks might be. So let's start by looking at something that we've seen in an earlier lecture. These are priorities for when you're trying to design for low energy or zero net energy buildings. And the first steps we've already done in the beginning of this class. This is where you want to do a good building, a good envelope, have good insulation, maybe thermal mass. We're learning now about shading and daylighting. And then we're going to, we talked a little bit about in the thermal mass lecture about passive solar heating. This is where you're using the sun to bring in the natural heat there. And now what we're going to be doing is talking about passive cooling. How can we naturally get rid of the heat? So since passive heating and cooling is about using natural means to mediate uncomfortable outdoor conditions and create comfortable indoor conditions, I want to do this little thing where we're going to just try to think about how do we describe how we feel in a hot climate, dry or humid. So the first thing I would suggest is just to get started, you need to get your phone and you need to text the word Gail Brager 190 to 37607. And that's how you're going to get started. All right. And then, let's see. So now what I want you to do once you've done that to get started is just, you can do more than one response. Use words. What words would you describe? What words would you use to describe how you feel in a hot climate, a hot dry climate, a hot humid climate? This is great. Keep them coming in. Just keep them coming in. Ooh, I like that, the sluggish. So it's not just a thermal thing, but it's how it actually makes us feel in terms of our alertness or fatigue. These are fabulous words. This is great. Dehydrated. So maybe, ooh, that reminds me, I'm going to have a little sip here. Sweaty. So it's not, there's a moisture component to this as well. It's not just hot and cold. Oh, I see the word heavy. That's really good. So we use words that aren't necessarily thermal, but they have analogies to how we might feel thermally. Claustrophobic, you know, it can be kind of just oppressive. These are fabulous. A few more. Wonderful. The idea of tired, that there's actually a relationship between the thermal condition and our alertness. These are fabulous. All right. We're going to move on from that. Thank you. Thank you. Those were great. So I mentioned that if passive heating is about a natural heat source, then passive cooling is about a natural heat sink. Right? So what are those heat sinks? One, the air. And when air is the heat sink, we call that natural ventilation, right? So that's where you're removing heat from your body to the air, from the space to the air, right? So natural ventilation has lots of different ways of providing cooling. We talk about bodily cooling, where you're actually trying to just make yourself comfortable by removing heat. And there's also spatial cooling, where you're trying to remove heat from the space itself. Now, another form of passive cooling is earth sheltering. This is where we're using the earth as our naturally occurring heat sink. And this is where you're trying to dump the heat from the space into the environment. So let's see, I just got, was that an old note you just sent me about, can everybody see the right screen here? Sierra, can you unmute and confirm with me?
Yeah, I think it's fixed now.
Okay, sorry, I just got a old note from Stet that we were seeing the wrong screen. All right, so we've got earth sheltering, where you're dumping heat into the earth as your natural heat sink. On the bottom left, we call this passive cooling strategy evaporative cooling. And here, the natural heat sink is water. And we've got this cute little picture of the dog in the mist, in the spray. But we've also got bodies of water, not just mists of water. And we've also got mechanical forms of evaporative cooling. And we're going to be showing all of those later as well. Whoops, went too far. All right, then the last one is a little bit more complicated we'll be talking about, and that's radiative cooling. And there, what we're talking about as the night sky being the heat source. So it turns out that the top of the atmosphere is really cold. That's the night sky, and the earth is constantly losing energy to the night sky, and that becomes the heat sink. So we know we've got hot, dry, and hot, humid climates. So the question I ask for you now is, which climate do you think has more options for passive cooling? So go ahead and text choices A or B. What do you think? You think you're going to have more options in a hot, dry, or in a hot, humid climate?
Yeah, I think that I just wanted to double check that it's activated.
I just pushed activated.
Okay, great.
Yeah, but you can always back me up if that's not working. I'm not, let's see. Let me close it and reactivate it. Oh, there we go. Now it is. Sorry, I misunderstood the blue and the white. See, I'm just learning now too. So thank you everybody for your patience. Look at this. So a lot more people are voting for the hot dry. Anybody want to offer a reason why? And you can do this by raising your hand, and then Sierra is going to monitor that and can unmute you. Clearly, there's a lot of people who think hot dry has more options. Who would like to offer a reason for that? Anybody? Come on, don't be shy.
Oh, Sam?
Hi. It seems like it'd be much harder to pull moisture out of the air to make people comfortable than to, I guess, either put it into the air. It just seems like it's much easier to cool down dry air.
Yeah, that's excellent. And that actually has a lot to do with what we just did with the word cloud. Is what is it about a hot and humid climate that makes us uncomfortable? It's not just the temperature, it's the moisture in the air. So if we want to be more comfortable in a humid climate, it's not just about cooling things down, it's taking moisture out of the air. And that's not the problem in a hot, dry climate. So if you look at the screen I'm showing now, this is the building bioclimatic chart. And you've all seen this before, right? And so with this, if you look on the left side of the building bioclimatic chart, that's the dry area. And if you look on the right side, that's the humid area. And remember, the building bioclimatic chart is about showing what strategies are likely to be most effective in what kinds of climates. So what you're seeing here on the left side, the dry side, this is where you're seeing evaporative cooling and mass, and these are it doesn't show earth sheltered, but that's part of the thermal mass, right? And evaporative cooling is about adding moisture to the air. We're going to talk about how that's more effective in a dry climate. And what do you see over on the right side where it's really humid? Pretty much natural ventilation is the only thing you can do. So you can see there that just from the building bioclimatic chart, it's graphically showing how you can have a lot more strategies in a hot and dry climate. So let's start with the hot, humid climate, all right? And what I like to do with these is first start by thinking about what are the characteristics of this climate. How does that make us feel? And what's our comfort response? What's our clothing response? And then how do you translate that to what a building response might be? So in a hot, humid climate, you generally have warm days and warm nights. I've mentioned this before when we talked about climate earlier in the semester. It's just warm all of the time. Right? We already talked about how one of the reasons it's uncomfortable is because all the moisture in the air. And when we had our thermal comfort lecture, we talked about the ways our bodies lose heat is by convection from the skin to the air and by evaporation from the moisture on our skin to the air. Well, if you already have a humid climate where the air is already saturated, you're not going to be able to evaporate the moisture from your skin very readily, right? So you're going to need a lot of air movement past your skin to strip away those saturated molecules right next to the skin and increase convective loss by blowing more air. Remember we did that exercise? Strip away the moist, saturated air next to the skin so that the perspiration can evaporate. So the clothing response, the personal response in a hot, humid climate is to keep out the sun but let in the air. You know, minimal clothing, let as much skin as possible be exposed to the breeze. And that's exactly what we do in a hot and humid climate. So what you're seeing here is clockwise from the top left, there's a picture in Cambodia, in Malaysia, and in, I think this is Darwin, Australia, and then the Indonesian boathouse. So I want you to open up and use the chat screen and write as many things as you see right now. What kinds of elements do you see here? Physical elements in the buildings. What are you observing? So if people could just start typing words, that allows you to be communicating to me. There's no wrong answers here. What do you see? We've got stilts, thatch roof, wood, open space, elevated. So the thatch is the lightweight material, which makes it permeable. Shade, right? Operable screens, large windows, so it's breathable, so the air can go through. Blinds, so things are movable, so you can control things, right? These are fabulous, right? So even though these are examples from all around the world, those are some common elements. So if the reaction we have thermally means that we want to expose our personal skin to the air movement, that's what we need to do in these buildings as well. So you have these lightweight permeable envelopes so that the air can move through them. You've got steeply pitched roofs because there's a lot of rain, so it's shedding the rain on the outside, and the steep pitch also gives you high ceilings on the inside so that you can have stratification and get that warm air above the occupied zone and then maybe vented at the top. You have a lot of wide openings and often protected in the lower right. You see these awning shades that can open up, and you can have operable windows that are still protected from the rain. So even when it's warm and humid and raining, the air can come through even though the rain is kept out. Now, why would that be elevated? Right? The structures in hot, humid climates are elevated for a number of reasons. There's a number of benefits. One, these areas probably get heavy rains and are prone to flooding, and that's probably the first reason that they're elevated, so that you can get above the flood area. I see somebody's written higher wind speeds. That's absolutely correct. So the wind is low at the ground, and it starts getting higher as we move up. So the benefit of being elevated is you get access to higher winds. You can get air under the structure, so you're actually cooling the floor of the structure as well, so you're not in contact with the warm earth. And hey, it's a shady place for your animals to hang out as well. So here's something fun. Let's try this one. And I want to thank Sierra, who is helping me with this poll everywhere for the first time. I think it should be activated. I'm pretty sure what you need to do here, though, is that you need to actually go to that website that's on the URL at the top of the screen, and you click on what areas of the country you think are hot and humid. Hey, it's working. Click, click, click. Keep going. We're going to have another one later in the lecture for the hot and dry. Good. Keep clicking for a little bit. All right. So what I'm seeing is that for the most part down here, this is generally the hot and humid region, right? Here it's a little bit more coastal, so it's more moderate. You get some humidity from the coast, but the real hot and humid regions are going to be down here in the southeast. So when we're trying to ventilate, what are the driving forces of ventilation? Okay? So in these cases, what we're doing in these diagrams is showing these little arrows, right, about where the air is moving. And just like heat flows from a high to a low temperature, air flows from a high to a low pressure. And that pressure difference can be created by two different things. So in the cross ventilation, the pressure difference is created by the wind itself. So on the windward side, think about that air piling up. There's a positive sign there, and that means the pressure is higher than your typical ambient pressure. And on the leeward side, it's negative. So you get this push-pull effect, and air enters on the windward side and on the high pressure and comes out on the low pressure side. And in the bottom right, stack effect. That's talking about the pressure differences that are created by the natural buoyancy of air. So warm air rises. And as the warm air rises, it's going to exit out tall openings. And as it does that, it's pulling air in through the lower openings. So designing for these two means that for cross ventilation, you want to put openings on both the windward and the leeward side, because you need a place for air to enter and for it to exit. And if you're designing for stack ventilation, you want openings on the low part of the building for air to enter and openings on the high part of the building for air to exit. All right, so here's another one. Which driving force do you think is likely to be stronger? And I'm going to hide the responses for just a moment so that you're being independent. Go ahead and click A or B on your phone. Let's see what people are doing now. Oh, look at that. All right, so it is based on circumstances. So that's why the question was intentionally written as which driving force is likely to be stronger. If you have any wind at all happening, the cross ventilation is very quickly going to outdo the stack ventilation. So A is the correct answer there. That is likely to be stronger. But you have a lot of circumstances where the wind isn't available. So when people are designing for natural ventilation, often what I've heard engineers talk to me about is that they first design the building so that it operates well with stack ventilation. So they imagine what's the worst case scenario when there might not be any wind available. And in those circumstances, is the ventilation still going to work? And then if it works for stack ventilation, then as soon as there's wind, it's likely going to work even better. So here's some classic examples in the US, in the hot and humid regions of the Southeast. Remember the lower right part of the map that you were all clicking on. These traditional houses were built with extensive porches, with deep overhangs, large windows. The living space was often considered to be more than just the interior. So there was a lot of emphasis that was put on protected outdoor spaces. The porch might be partially enclosed with lattice work to provide privacy and shade, or it might be open, very tall windows that can be open fully, tall windows that are high up, these dormer windows up above so that you can take advantage of the stack ventilation. And you can also see this building is elevated, just as we saw from the traditional dwellings I showed earlier. Oops, that was not supposed to happen. There we go. So here's another example, the Waverly Plantation in Mississippi. What you see here is this really large central atrium where the air is going to gather and then be ventilated out the top. Another traditional form in the US for the hot and humid regions is the dog trot house. This was developed in the Appalachian Mountains, and the idea here is that there'd be a single opening, a breezeway, and as the winds would blow through the breezeway, the acceleration of the winds would create a low pressure zone. So it turns out that as velocity goes up, pressure goes down. So that would create a suction zone through that breezeway, and it would pull air through the surrounding rooms, and then it would leave through the breezeway. This is an example of a more contemporary building that followed the example of the dog trot house with a central breezeway combined with this need for stack ventilation. And you might remember that there was a model of this house in the wind tunnel when you did the building science lab. And this was something that another school had tested and then sent us the model to be able to use for ourselves in the wind tunnel. So what you're seeing here is an example of the cross ventilation. So you have windows on the windward and the leeward side, and stack ventilation, which means you have low and high windows. Now, this is a lovely little building that also was an interpretation of the traditional dog trot style. The architect here, Stephen Atkinson, is from Baton Rouge, Louisiana, but his practice is actually here in Palo Alto. And he did this small house, which was got several awards, a very small house for a couple that was recently retired. They wanted a weekend home that was modest, that they could build their own on their own. So he used really simple materials and construction techniques. They wanted something that would make them feel connected to the land, and they wanted something that was in the tradition of the surrounding rural architecture. So on the exterior, he used a lot of corrugated metal that is reflective of the local agricultural outbuildings, and consistent with the dog trot style, you can see this central breezeway that is then connected by these rooms on either side. Here's some more drawings of that. On the upper right, you can see that central breezeway that becomes a commonly used living space. It allows for outdoor living that still protects you from the elements, and it separates the public and private rooms on each side. You can also see the picture on the upper left gives you a sense of why this was also sometimes called a style called the shotgun house. And it refers to this narrow rectangular plan where rooms are arranged one behind the other. And it's this very strange, in my mind, reference to the idea that if you fired a shotgun into one side of the house, it would fly clearly through and out the back. So maybe that's Louisiana kind of cultural. So the other thing I want to point out is if you look at the breezeway, it's this really nice, it's much bigger than the traditional dog trot, which it created a much larger space for social outdoor living. There's these sets of glazed doors on either side, so it allows a lot of light to penetrate on both sides of the house. But outside of the glazed doors, it also has these corrugated metal shutters that would allow the house to be completely sealed off when the owners aren't there, since it's just a weekend home. All right, so another house I wanted to show you is done by Glenn Murcutt, who does all of his work locally in Australia. He's a wonderful architect. If you want to look up more of his projects, he won the Pritzker Prize in 2002, which is a very coveted prize in the architecture field. And I wanted to show you the Magny House, which was built in a temperate climate. You can see in the map on the upper right, it's on the southern coast of New South Wales. And the clients here had owned the land for many years. They used to go and they used to use the land for camping holidays. And they really wanted a house with a tent-like quality, strong connection to the outdoors. So the building, you can see, has a very long linear plan divided by a central courtyard, which I'll show you a close-up of shortly. It can operate as either two self-contained suites with one parents on one side, the other for guests or families. Because remember, this is Australia, the Southern Hemisphere, so the sun is in the north. So the main facade and living spaces of the house face the north, which is like our south. And you can also see, I'll show you a close-up in the next picture. You can see this inverted butterfly roof is over the internal corridor, and that supports this big oversized gutter that collects rainwater and is connected at either end to two large downspouts. So here you see the picture on the right shows the north facade, again, like our south, and it's designed with a lot of different layers. So at the very top, you'll see this upper clear story window, and that is great for bringing in a lot of natural light. and it's shaded by a very large overhang that is designed to provide 100% shade in the summer, 50% at the equinoxes. You know how to do that. You're doing that now in your design projects. The lower glazing on that main wall is all operable. There's sliding glass doors. There's screens of individually adjustable and retractable external louvers. Now, if you look on the picture on the left, what on the far left, the thinner part of the building is the service corridor. And when I show you the interior, you're going to see that the lower part here is solid because that's where a lot of the services are. And I want you to notice on the upper part, I think you can see my cursor there, that this upper part of the wall is slanted out. And what that does is it allows this little horizontal lip here. And that enabled not only these larger windows to open on the angled wall, but in that little horizontal lip, it allows for these horizontal vents to be able to help facilitate ventilation. Here's just a close-up of the gutter that captures the water. And then here's the interior. And so a couple of things you can see on the right side of this picture. You can see that's the service corridor, the upper windows that are slanted. And what's interesting here, you can see how the interior walls only go up to the door height. And then it has this interior clear story glazing above. So that's really good for light. And it's also is a way to make the roof feel like it's just floating over the structure. And it gave it this tent-like feel to it. And then the last picture of this house, you can see the veranda that connects the two sides of the house. Right, so the next building I want to show is the 16-story Torre Cube, which is a landmark tower in Mexico. It's spelled like cube, but it's pronounced Cube, which I understand is actually derived from the nicknames of the architect's two main clients. And it's built around these three concrete piers that are the main structural element of the building. And then these cores work as columns. They also, they have the vertical structural support. They also contain all the facilities and vertical circulations. And then from those main concrete shafts are cantilevered steel girders that support these trapezoidal floor slabs for the office modules. And then what you can also see that I'll show again in the next picture, that a number of these stories, you see these gaps, and they're emitted at various heights in each of the office wings, and it creates these breaks that allow light and natural ventilation to enter the atrium. The building relies entirely on natural ventilation in a very hot climate, and then by eliminating the HVAC equipment, it also eliminates the spaces needed to house that. So the building has a double skin facade, which we're going to talk about in a little bit more later. It's got this central atrium that extends over the full height of the building, that's open at the top so the air can move through these large gaps up the atrium, and utilizing the stack effect. That rising stack of air is then going to pull the air through the lower openings on each office floor. So it's not that unlike a thermal chimney or the chimney in your fireplace, that as the heat of the fire rises, it pulls the air through the fireplace and up the chimney. You can also see that the exterior is composed of this lattice work of wood. It's got sliding walls and operable windows, and enables you to get access to that space between the glazed facade and the outer screening layer. Here's some pictures from inside the central atrium and also looking up. And the diagram on the lower right there shows different floors in the building and how these openings rotate around. And it's interesting, this building is really similar to the Commerce building, Commerce Bank building that was actually done 8 years prior to Torrey Cube, but it's a lot of similarities in form, where you've got this triangular plan, you've got this spiraling of openings on that are each 4 stories tall, but they rotate around the building, and they provide a lot of light to all of the interior offices. And here's some other views of that. You could see that in each of these gaps, they have a lot of plantings. They call them winter gardens, and it allows a lot of light to come in, and it has this large central atrium for stack ventilation, and it allows you to kind of see across from the gardens into the other offices, and from the offices into the other gardens. So this is what we call a mixed mode building. And mixed mode means you're combining natural ventilation with some form of mechanical cooling. So in this building, I've seen reports that show that natural ventilation is working about 60% of the time. And when the HVAC kicks in, they're using a chilled radiant ceiling, which we'll be talking about later in the class. And it's got a double skin facade, which I'm going to show you a little bit more about. And the idea of a double skin facade is that you've got, it's not just like a double skin window has a really small gap. A double skin facade has a functional plenum space in between the inner glazing, which is usually double glazed, and the outer glazing might then be single glazed. The double glazing is usually on the inside, because that's where you're going to have the biggest effect on the surface temperatures of the inner glass, which is then going to affect people's comfort. So within that plenum, you generally have operable blinds, and that plenum also has vents. Now, there's lots of different ways these double skin facades can be designed. That facade can just be capped on every floor, or it can be much taller, and so the plenum actually has a much taller stack effect. But the key thing about these double skin facades is that they can be operated in a number of different modes. So for example, in the summer, the goal is to keep the heat out. So the way you might operate it is to put the blinds down so that it reflects the sun, minimizes how much heat gets into the building. And then you keep the inner pane closed, and you ventilate that space to remove any heat that's accumulated. Now in the winter, you have the opposite goal, right? You're trying to bring the heat in. So in that case, you might open the blinds, let the sun come in, and you might close the vents on the top and the bottom, so you create this insulated buffer space. And then there's all kinds of ways that you can operate this differently in the mid-seasons, in passive mode. So you might close the blinds to keep the sun out. You might open the vents to ventilate that space, but you could also open the windows so that that air is actually not just ventilating the plenum, but it's actually moving into and ventilating the interior office space. And maybe you, in those mid-seasons, you can turn off the heating or air conditioning entirely and create just passive mode. All right, so here we've got another poll. What do you think is the most common reason people might decide to use a double skin facade? So here's our choices. The aesthetics. It allows you to do an all glass facade rather than punched windows. The buffer space provides sound insulation from the exterior noise. Better winter comfort, because if it's really cold out, your body's not exposed to a cold surface. That buffer space gives you much better insulation, or it allows you to protect the shades so that you can have them on the outside of the inner skin, but they're not exposed. So, what do you think? Well, I'm saying first thing I'll say is that all of these are reasons. The double skin facade does do all of these things. So there's not a wrong answer. The question was clearly written as, what do you think is the most common reason? And I don't know for sure, but I've talked to engineers, and I will say that D is not the answer I get from people. It does that, but it's not the most common reason. So try some other guesses, knowing that, yes, it does do D, but that's not what's motivating people to do it. Any other guesses? That means everybody who voted D should guess something else, and I should see that bar going down. People are still sticking to it. That's my answer. I'm sticking to it. All right, there we go. Okay, there's a comfort thing. Okay, so here's what people have told me. And again, I'm sure it's different in every case, but people have told me it's A, which surprised the heck out of me. That people want the appearance, the glass curtain, the all glass facade, but so that's the starting point. That's the most common reason. That's their starting point. But in order to get that all glass facade and still have good performance, then they go through all these iterations. Can we just do high performance glass? No, it's not good enough. Can we do this and that? And then they get to the double skin facade that allows them to have that exterior appearance while still doing all of these other things. All right, so I'm going to, while we're taking just a couple minutes stretch break, I'm going to ask people if you have any questions. And Sierra, I'm going to ask you to monitor that. And you can, let's see, there's a couple ways you can do this. You can add a question on chat. You can raise your hand, and which I like, because then I like to hear people's voices. And then Sierra can call on you and unmute you. It could be questions on double skin. It could be questions on anything I've talked about so far. No? Not seeing any hands. I'm not seeing any comments. All right. We will keep going then. So now let's move to the hot, dry climates. And what are the characteristics here? Let's start again with the climate characteristics and then what the comfort response might be. So the climate characteristics of a hot, dry climate is that it can be really, really hot. Humidity's low, but the temperatures can be easily in the 90s, easily over hundreds, right? Sun's beating down, a lot of clear skies. And so the most important response for comfort control in a hot and dry climate is to protect your skin from the sun. So having clothing that may fully cover your skin, but it could be, you know, lightweight, that's the same, and white to reflect the sun, that's the same kind of thing that we need to do in the hot, dry vernacular response or climate responsive features. So let's do the same kind of thing with chat. If everybody can just type in words of what do you see in these, what do you see in these examples? Go ahead and just type in some words in chat. All right, so now we're seeing a lot. People are noticing the thick walls, the massive materials, right? The open courtyards, the water for evaporative cooling, right? Did anybody mention that you said what about the roof shapes? We see the dome, but you also see a lot of flat roofs, right? Earthen materials. Good. Smaller openings in these. So the classic response in a hot, dry climate is that you need to protect yourself from the sun during the day. So you're going to have these massive materials. You're going to have smaller openings. Another characteristic of a hot, dry climate is you've got hot days and cold nights. So the strategy for natural ventilation is going to be to soak up the heat during the day in that mass and release it at night. So you need windows that can be closed down during the day and opened up at night. So the windows on the outside are going to be very small. You might notice here there's larger windows on the inside. So if you have a shaded courtyard where you're not getting a lot of direct sun penetration, those windows might be larger. So you've got the mass, you've got the windows that can be closed during the day, opened at night, courtyards and the use of water for evaporative cooling. You see in the lower right, we'll talk about these wind scoops and thermal chimneys for bringing in air to lower spaces. And then the flat roofs are a way of having radiative cooling to the night sky, which we'll also be talking about. All right, so let's do the same thing. Go to that website and click on parts of the country where you think it's going to be hot, dry. What do you think? Yeah, so everybody's going more towards the west, a little bit more towards the south. Right, those are all great. All right, so if we look at a map of the US of how we characterize climate zones in a very general way, in general, the hot, dry areas are going to be in the southwest, the hot, humid areas in the southeast. That doesn't mean you're not going to have hot, dry conditions or hot, humid conditions in other places, but the way they do these broad characterizations are going to look like this. Now, the other thing that's kind of interesting about the US is that we have something that has been referred to as the Sun Belt, which is that whole southern region. And the Sun Belt saw huge population growth in the 1960s. And a lot of that came out of the increase in availability of air conditioning in the late 1950s. So people were seeking a warm, sunny climate, but you couldn't really exist in those areas very easily and have large commercial buildings and manufacturing without the use of air conditioning. So we're going to learn more about the evolution of air conditioning in a later lecture, but it was really in the 50s and especially the late 1950s when it was available for residential applications, and there was massive advertising. And it was this advent of air conditioning that enabled people to actually move to the Sun Belt areas and be able to have more manufacturing and industry and economic growth. So let's look at what some of those passive cooling strategies are in the hot and dry areas. So we mentioned that in hot, humid, pretty much only natural ventilation works. Now it also works in the hot, dry climates when it's combined with thermal mass or earth sheltering. So we've talked about thermal mass before in this class, so let's focus a little bit on what we mean by earth sheltering. Earth contact cooling, I should call it, is actually two different categories. It could either be earth sheltering, where you have direct coupling between the house and the earth, or what we also call indirect coupling. And there's these things called earth tubes or earth air heat exchangers, where you're burying these tubes deep in the ground and you're bringing air in. And it turns out, I'll show you in a graph, that the earth is cooler than air temperatures in the summer and warmer than air temperatures in the winter. So if you run air through these tubes, it will naturally heat or cool that air. This is a diagram from Sun, Wind, and Light, where it shows just these different typologies of earth sheltering, where you're either building directly into the ground or you're building above the ground and then you're berming the earth up around it. So why does earth contact cooling work? Here you see a graph of soil temperatures as a function of depth. The x-axis is time, the y-axis is temperature. And these graphs should look a little bit familiar to you, right? These graphs look like what we showed in the thermal mass lecture at the very beginning of the semester. What happens is you have more thermal mass. There's two effects, remember that? There's a dampening of the magnitude and there's a shift in the magnitude. So you're seeing that same thing here, that the further down you go, there's both a horizontal shift in when that peak occurs and a vertical shift in the magnitude of those peaks. And that's because the further down you go in the earth, the more effective mass you have. And there's a rough rule of thumb that you get about a week per lag. A week per foot in terms of lag. So here's an example of an earth sheltered building that I think really gave earth sheltering a bad name. This came out of the bomb shelter mentality in the 50s. It's an entirely underground house in Texas where they thought, no problem, we'll just pretend we're outside and we'll bring all the elements of the outdoors down below. We'll paint these murals, we'll put in a picket fence, we'll put in lawn furniture outside, and it's really pretty ridiculous. And the reality is that most earth-sheltered buildings can have as much glazing area as an above-ground building. It's just focused and concentrated. So here's two examples that do just that. The upper left is a hillside home in Kansas. It's a sloped hill, and so it's cut into the hillside, and there's a lot of glazing on the south side of the building where it should be. So it gets a lot of natural light that then is bounced further back into the space. The lower right picture is an interesting one. This is also on a hillside, but it's a community of earth-sheltered buildings that step down the hill so that the roof of one home then becomes the front yard of the home above it. And so each one steps down, and each one has exposed glazing and outdoor space. Well, earth sheltering isn't only used for residential buildings. Here's an example of a library where earth sheltering is being used to cool the lower floors and the atriums. So there's a courtyard that's dug down into the earth, and then the rooms surround that courtyard. All right, so the next topic I want to talk about is earth and straw bale, but I'm going to pause for a moment to see if there's any questions. Sierra, if you want to help me monitor if there's any questions with hand raising, or if people want to add a chat. I see somebody from Phoenix can confirm.
Oh, Jasmine?
Yes.
Hi, yeah. So for, I guess, earth sheltering, isn't it more expensive to, I guess, build right underground? And I guess like how do architects sort of deal with sort of that, cost trade-off?
So the question was about the cost trade-off of building underground, and that's interesting because there are trade-offs. On one hand, there are added costs for excavation. On the other hand, there's cost savings because you don't have as much facade treatments that you're having to design for. So you get some savings there and you get other costs. It's probably very dependent on circumstances. But there's both additional costs and also savings. Good question. Anything else?
Thank you.
Maya?
Yes.
Are those houses built into the earth? Are they like optimal in a certain climate, or are they good for pretty much all climates?
Oh, excellent question. So if you remember when we talked about thermal mass works best when there's hot days and cold nights. Well, for earth sheltering, take that same thing, but on an annual basis. And it turns out that if you looked at that graph that I showed, and this is such a good question, I'm going to go back to this picture here, all right? So if you imagine the further down you go, the temperature of the earth is going to start being relatively constant. And it's going to be about equal to the average annual air temperature. So let's think about that. In a hot and humid climate, what's the average annual air temperature? It's warm in the summer, it's warm in the winter. So the average annual air temperature is going to still be warm. But in a hot, dry climate, which is what this picture is showing more about over the course of the year, you have hot summers, cold winters. So by the time you get that average annual air temperature, that ideally is right around the comfort zone. So this is primarily for a hot, dry climate. Did I see another question?
Yeah, Shoja?
Hi. Yeah, I was wondering in like seismically heavy areas, especially like California, is it common to do earth sheltered kind of buildings, or do they try to stray away from that just in case?
Yeah, that's a good question. I think that's a great question, and I don't know the answer to it. California is, in terms of climate, is really not as hot and dry as where you'll see most of these earth sheltering buildings. But that said, some of those other areas may be have high seismic activity as well. So if one of the GSIs can send me a note to remind me, I think that's a great question, and I'm going to look into that and see what I can find out. All right, so earth can be used as a veneer around straw bale. So straw bale construction usually combines both the straw bale for heavy insulation and some kind of plaster on the outside, which aids in the thermal mass. So the thing about straw bale, the straw that's used in straw bale is a waste product, which is usually burned in the fields and creates a lot of pollution. So not only is straw bale construction good thermally, it's also good environmentally because it's taking a waste product and giving it some other use. The thickness of these bales, they're generally at least about 18 inches thick. So they have very high R values. They're trapping a lot of pockets of air. So R30 to 50, I've even seen higher numbers reported. Now, during construction, it can be a fire hazard because you've got a lot of this loose straw on the ground. But once the building is built and it's very dense and you've got the earthen or plaster finish on both sides, then it's considered to be fire resistant. And one of the phrases I've heard about the strategy for straw bale construction is you need good shoes, a good coat, and a good hat. And that refers to the need to have a really good, sturdy, damp-proof foundation, to have some kind of stucco or earthen plaster, and to have a big overhang on the roof that protects the walls. But these have been known to last for a very long time. Here's a few local examples. This is Dan Smith Architects. He's a local guy, and also Bruce King. So we've got, and David Arkin. Those are three names of local architects who do a lot of work with straw bale. So if it's something that you're interested in, I encourage you to look up their names. This was actually a little home that was built after the 1990 Oakland fire. And this is another local building, also done by Dan Smith. that you can visit. It's in the Shorebird Nature Center down in the Berkeley Marina. So it's a public building, and they have a lot of displays inside that teach you about how the building was constructed. Another, maybe about an hour away, I think, the Real Good Solar Living Center in Hopland, California, was done by Sim Vanderen, who used to be a professor at UC Berkeley. And this is a lovely building with a lot of different passive features. One of the things I want to point out, because I'm going to show you in the next slide, is look in this upper left picture. You see how the roof is stepped down? This is a wonderful daylighting strategy with these steps that I'm going to show you in the next picture. And this is a very early aerial photograph that was done by former Professor Chris Benton. He does a lot of kite aerial photography long before we had drones. So he's got some really wonderful pictures there. So very early, and there's a lot of vegetation that was built up on this structure here. So that's an outdoor shaded space. But let me show you on the inside, this upper left, I said to look at how the roof was stepped down. Every time the roof stepped down, that vertical distance was glazed, and it's a wonderful way to bring in daylight and wash the ceiling with daylight. Those are also operable, so it allows for stack ventilation. You can see here these large windows and these panels that come down. The lower left has a close-up of that, and these are these insulated corrugated panels that are very reflective. They serve as light shelves during the day, and at night these cables bring them up, and then they insulate those glass panels. And what you see on the lower right here is every straw bale building, the tradition is to have what's called a truth window. And that's this idea that straw bale buildings, once you put the plaster or earthen veneer on, you don't know it's straw bale. So all of these straw bale buildings have this cutout somewhere inside so people can see the layers of how it's constructed. Now, the other reason I wanted to show this building, hold on. Oh, so this building was actually studied at length by a former 140 GSI, Adam Jackaway, who was doing his thesis here at the time that Sim Vanderen was designing the building. And he used a lot of the tools that you're learning now in 140 to do shading and daylight modeling. And he had a big influence as a student on the design of this building using the very tools that you're all using now. He also did studies in the wind tunnel. And so that's where he was able to do flow visualizations and also velocity measurements to see how the cross ventilation was working. Wind tunnels don't study stack ventilation, but you can study the cross ventilation. All right, the next thing I want to talk about is evaporative cooling. But are there any questions on the last topic before I move on?
It looks like there's a question on how long straw bale buildings last.
I have been hearing that they last hundreds and hundreds of years. They're all over the world. So it's, and that and the earth buildings. So once they're constructed, they last for a long time. All right, so I'm going to move on to evaporative cooling. So the idea of evaporative cooling is where you're using water as the heat sink, right? So one of the most common ways to use evaporative cooling is simply through gardens and vegetation, right? So that the plants themselves are going to have evapotranspiration. They are going to give off moisture. And we talked in previous lectures about phase change, if you remember that when moisture evaporates, it goes to a higher energy state. And so when you go to the higher energy state, you have to absorb heat from somewhere. So you're absorbing it from the air itself. So when you add moisture to the air, the evaporation process is cooling that air. So you can do that through plants, you can do that through pools and fountains. So an important point I want to make about these two pictures is that just like, remember our equation of UA delta T, heat transfer is proportional to a surface area. Same thing with moisture transfer, proportional to surface areas. So on the left picture, the surface area is basically the surface of that pool. In the right picture, when you have a fountain and you're spraying a fountain or mist into the air, the surface area is actually the additive surface area of every droplet of water. So spraying water into the air is going to be much more effective than just having a still pond. Now, we also can use evaporative coolers as a mechanical system, and this is often thought of as a hybrid system. And hybrid meaning it's not mechanical cooling in terms of using the compressive cooling cycle that we're going to be talking about during our HVAC lectures, but you are using some energy for the fan. And the idea of how an evaporative cooler works is that you start out with hot, dry air, and you introduce water into that air. You either spray water or the air flows over a sponge or a pad where there's water in it, and that water evaporates into the air. So you start out with hot, dry air, and you end up with cool, moist air. And when you do that, you actually haven't added or removed any energy from the air itself. And so for that reason, this is called a total energy, or the enthalpy process being constant. It's a zero enthalpy process. It's also called an adiabatic process. You're not adding or removing any energy to the air. What you are doing is you're exchanging how much of that energy content of the air is due to its temperature, which we call sensible heat content, or due to its moisture, which we call latent heat content. So you're trading hot, dry air that has a large sensible heat content to cooler, moist air that has a larger latent heat content. But the total energy or enthalpy content of the air is constant, and that's called adiabatic. Another local example that you actually saw an example of this in the wind tunnel as well when we did our tour is the Orinda City Hall, done by local architects Siegel and Strain. They have these evaporative coolers. They're also sometimes called swamp coolers, but I don't recommend that name because I think it gives the wrong impression. I think it's one of the reasons people have steered away from it is just the terminology we've used for it. This building uses evaporative cooling. It also does a lot of cross ventilation, and that's why you saw the model of it in the wind tunnel. That's what we were studying. Now, another way to use evaporative cooling is through these evaporative cool towers. And the idea here, again, is to start with evaporation, that you're spraying water into the air, probably at the top of the tower. And as the air cools, it's heavier. We know that warm air rises and cool air is more dense and it falls. And so by spraying water at the top of these cool towers, the air naturally becomes heavier and falls, and you get this cooler, moist air coming into the building. Here's an example of evaporative cool towers gone wild. I've never seen so many on a single building before. This is in Ahmedabad, India. And what's interesting about this is that it's really a combination of the evaporative cool towers, which is shown here as the blue tower, and also something I'll show in a moment, which is a thermal chimney. So the evaporative cool towers, by using evaporation, it shows this mist at the very top, the cool air falls. But these thermal chimneys, which I'll show shortly, is a way of letting warm air rise. So you get this double effect where some of these towers are bringing air down and some of these towers are bringing air back up. All right, the next one I want to talk about is radiative cooling. And the idea here, I had mentioned this before, is that the very top of the atmosphere is very cold, and our planet is constantly, the way our planet maintains its heat balance is that there's incoming solar radiation during the day, and 24 hours a day there's outgoing radiation to the cold night sky. So, but it's only having the balancing effect at night when we're not getting the incoming radiation. So what we're trying to do is take advantage of the same way that the planet is losing heat to the outer atmosphere and that cold night sky, and do that in our buildings as well. So one of the systems that has taken advantage of this is a roof pond system. That's the generic name. SkyTherm is kind of a brand name for it. And what you see here is you have to have a flat roof, and that's both because it gives you a larger view to the sky, and it's basically like putting a waterbed on top of your roof. So this is not a retrofit strategy. You need to have designed this from the beginning. The idea here is that you have these water-filled bags on the roof, and then you have these moving insulation panels that cover it. And then you have a very good conductive contact between the bags on the roof and the space below. So this picture shows a corrugated metal roof below the water bags. So the same system operates differently in the day and night, and operates differently in summer and winter. So in this picture, I'm showing you the summer operation. So during the day when the sun's out and you don't want the sun, you cover it with these panels, which are going to have a very reflective outside coating. And then at night, you open up the panels, and these water bags are losing their energy to the cold night sky. And it's kind of a combination of using radiative cooling and also mass, because we know that water has really good thermal mass. So it radiates to the cold night sky, it cools down, and then in the morning, the upper picture, you close the panels, and then you have this very cold ceiling above you, and all of the heat from inside gets sucked up into that ceiling. And then in heating, the top two pictures are exactly the opposite. You would open the panels during the day, and you would soak up the solar radiation. And then at night, you would insulate and close the panels. So the same system works both summer and winter, but the day and night cycles are reversed. Here's just a close-up of one system. You can see the water bags exposed, and then the sliding insulation panels on the right. And although this is not a very common system for a whole lot of reasons, I think people are very wary about putting so much water on your roof. It actually, in terms of thermal performance, these systems work really well. So here's a measured performance in the summer. You can see the outdoor temperature swing getting over 90 degrees at night and down into over 90 degrees during the day, and down into the 50s at night. And look at the indoor temperature, almost constant at 70 degrees all day long. So thermally, it's admittedly a pretty amazing system, even though it is not very common. All right, to finish up with a couple of things here, we can combine natural ventilation and thermal mass with this idea of thermal chimneys. And the way that thermal chimneys work is you see these examples in traditional dwellings where you have a very tall tower. So the height is what's going to give you the stack ventilation effect. You've got heavy mass, so you're going to have a delayed effect. And then you've also got openings for the sun to come in. And the idea here is that the solar radiation is going to heat the air in the chimney. The mass is going to have some delayed effect. So by the time that heat reaches the inside of the chimney, it's going to be evening. And then as that air rises in the chimney due to the stack effect, it's going to pull in the cooler air from below. Now, there are more contemporary versions of this that replace the height of the stack with higher temperatures, maybe having a solar collector on the roof so that you still get the same stack effect, which is a combination of a temperature difference and height. So they trade the height for the temperature difference. These are some drawings from Sun, Wind, and Light that show the different operation during the day at night. And it's showing that in the earlier part of the day, people are combining this with migration and where they're spending time in the space. So during the day, the mass has been cooled all night and it's cooler during the day. People go down below. And then by the time the evening happens, the chimneys have warmed up and then the heat is starting to rise and it pulls the air through the house. And then also in terms of migration, people will spend more time on the roof at night so that they get the advantage of radiative night cooling as well. And then I will just end with a few examples of some traditional buildings, not some traditional buildings, some historic buildings that have used this traditional response. So the BRE building in the UK used it in a really interesting way where they combined these thermal chimneys with, you see these glass walls, and the glass block was a way of bringing in more sun and heating that up. But they interspersed those between the glass block, which is translucent, and these panels of clear glass so that people could see through them. And then this is a section where you're seeing the ventilation is by the air rising through stack ventilation in these chimneys. It's pulling air in through the lower windows in the office space. And then my last couple of pictures are just from the Inland Revenue Center in the UK by Michael Hopkins, who's a wonderful architect. I encourage you to check out his work as well. And one of the things that's really unique about this building is that the thermal chimneys were in the corners of, there's like 7 or 8 buildings on this campus, and the corners of the building were these large thermal chimneys with glass block again to be able to collect the sun. But those were actually the circulation space. So it was really wonderful. These became occupied thermal chimneys with these beautiful spiral staircases. And yes, these spaces became quite warm, but because they were transition spaces, they were circulation spaces, and because they were in the UK, which may often be cold and overcast, it was sort of a welcome moment to be able to use these overly warm spaces, but it was just for circulation. You weren't using them all the time. So that is my last image, and I will, you're welcome to leave or you're welcome to stay on the line, and I will be available for any questions people might have. So thank you. Oh, this is so weird talking to a screen, but thank you anyway. All right, so I'm going to open up, let's see, a couple of ways. You can, again, you can raise your hand. You can type questions in on chat. And Sierra and I are going to both try to monitor those. Let's see, and I'm having some monitor problems here. There we go. Okay, and I saw some earlier questions about roof ponds on, yes, hot, dry climates. Now, one of the reasons they work on hot, dry climates is because they're radiating to the night sky. What happens in a humid climate? You have a lot of cloud cover, you have a lot of moisture molecules in the sky, and so you're going to not have exposure to those cold temperatures as much. There was another question I saw, yes, from Sierra to everybody, that yes, that some of them are open, and I've seen these, you can spray the top of them, or have these bags open, and then you're actually using evaporative cooling combined with radiative cooling. I think we showed the Carnegie Center for Global Innovation at Stanford does an evaporative cooling system on the roof. Let's see. Somebody asked about if there was an update to the design project. And as a matter of fact, yes, late last night, we posted all of the newest assignments for the next few weeks. So you can go ahead and check those out, and GSIs will be talking about them in section. Let's see, somebody else asked about, oh wait, what material is the water held in? It's some kind of, it better be really super heavy plastic, because you do not want those to burst. And I think that's what makes architects a little bit nervous putting that much water on the roof. Can you briefly go over the new changes, design project, and quizzes? Well, the GSIs will do that in detail, but really high level. And again, you can see all of the handouts. The main change to the design project is that all of the tasks will be done individually, and you will use your team for collaborating and sharing and talking and making decisions, but it was unrealistic to ask you to actually do the tasks together. So we broke it down into individual tasks, and we broke it up so that there are some options as well. So in weeks 12 and 13, you can go ahead and see that there's a lot of options, and then you as a team need to decide which options you're going to do and how you're going to divide them up. Quizzes, yes, we are having quizzes on a weekly basis, and the first quiz is Wednesday, and I believe we're going to be using Gradescope for that. So stay tuned for more details about that. Another question, changes about the final exam. I have no friggin' idea how we're doing this final exam yet. Faculty all over campus are talking and sharing ideas about how we are going to do it. So I don't know the answer to that, but as soon as I know, you will all know. So that's to be determined. Great question. I wish I knew the answer. Any other questions? All right, with that, I'm going to end the meeting. And again, thank you. I hope you are all well. Please, please take care of yourself, not just your physical health, but your emotional health. These are difficult times. Please get out in nature. It helps. All right, so with that, I'm going to end the meeting, and thank you.